Welcome to another open learning session. We will just continue where we left off the last time. It is inverse and transpose of matrices. We have done the multiplication and addition. So let's just jump straight into it. Okay, it starts with a definition. Inverse. Consider a square matrix A from with the dimension nn. Let matrix B be the same dimension, have the property that A times B equals the identity matrix, and B times A also equals the identity matrix. B is called the inverse of A and denoted as A to the power of -1. Unfortunately, not every matrix A possesses an inverse A -1. If this inverse does exist, A is called regular, invertible, non-singular. Otherwise, singular, non-invertible. When the matrix inverse exists, it is unique. When the matrix inverse exists, then it is unique. There are no two different matrices which can inverse one given matrix. In section 2.3, we will discuss a general way to compute the inverse of a matrix by solving a system of linear equations. Okay, so that's interesting. It is possible to use our beloved system of linear equations to compute the inverse. Remark: existence of the inverse of a 2 times 2 matrix. Consider a matrix like this. Okay, this is our matrix. If we multiply A with this matrix, basically they just flip. They flip the entries. We obtain a new matrix. Okay, we obtain a new matrix, and this new matrix is some kind of a scalar of the identity matrix. We can see that we have a 0 here and here, and the identity matrix always runs on a diagonal. It is 1, and the rest is zeros. And this is the case here. And even if we would have, I think, here is 0, the scalar could be something like, oh no, it is the same. And yeah. So even if everything is 0, if the scalar is 0, then it would be still true, because I could compute that. Okay, let's clean up a bit. Okay, so let's just take a look at this part. What have they done? They inverted these two elements, and they flipped the diagonal. Okay, so if we do that, then we will get this matrix. Okay, so I think we can just accept that. I mean, even if you do the computation or by hand, we will still derive here to this point. By flipping these two, we will get a 0 in each of those. And by flipping those two, what's happening is that these terms become equal. Because one time we start with the A11, and then like for this matrix, and for this matrix we start with A22. So in a 2x2 example, then this will have the same term. That makes sense. What I don't really understand is this part. So what are they doing? So they said that this one is the inverse, right? We know I think this equation here is essential. That one is the same as here. You can see that AB equals the identity matrix. And here we have A, you could think as, okay, so the problem here is that we have the scalar. This scalar. This scalar is missing in this matrix. That's why they put this scalar here in front. And if they put it in front, we get exactly this one. So if we put that scalar in front, then this equation would equal to just that one. There's another exception or condition, only if that is not equal to 0, because we are not allowed to divide by 0. And there's another thing, they say exactly this part is the determinant of the 2 by 2 matrix. Okay, so this looks more like a trick. I'm sure there is intuition behind it, but I'm just not getting it. I still remember that the determinant is somehow the space, I think. Like you have a vector, and then if you do matrix multiplication with that vector, then the vector is basically stretched in space. And let's say there's like a unit 1, and then it's stretched into a plane of unit 2. And this, I think, this conversion from 1 to 2, this is the determinant. So it gives us like a measure of how much space is stretched. This is what I remember. Something like that. But this is not helping us understanding what's going on here. It just says that this one is the determinant of this 2 by 2 matrix. And we can use that to check if the matrix is invertible. Okay, this definition is important. Also, that we are calling them invertible and non-invertible. I think this is also important. If it exists, it's unique. The determinant, I think we can skip it. It will come later and anyway. Okay, example 2.4, inverse matrix. The matrices A and B are inverse to each other since A times B equals the identity matrix and B times A also equals the identity matrix. Maybe this is a good point to do some exercise. Let's just calculate it. So I just copied it to this board. Now let's just write it down. Okay, this is a lot of writing. I'm not sure what's the easiest way to write this. I think I will just do a big matrix. Okay, I just gave myself some space, 9 blocks. And then we start with this one and that one. Okay, I just calculated the first one, it's 1. So the second one should be 0. Yeah, so it's 1. No, sorry. Blue goes, not blue, but yellow goes 1 to the left. And then we have minus 14 minus, what is it, 28. And then plus 42, right? How much is this? It's also 20, it's 42, so it should be 0. And then yellow goes 1 to the right again. Then we have minus 7, minus 35, and then we have 42 again. So this equals to 42, so it's 0. So what will happen now is we put yellow back here, and green goes down. So let's do it again. It's 2 plus 4 minus, what is it, 6, minus 6, right? So this one is 0. Then we move yellow 1 to the right. Then we have 4. Then we have 4 again. And then we have minus 7. This is 1. And then we move yellow to the right. Then we have 2 plus 5 minus 7, which is 0. Okay, that's good. So let's move that one down. So what do we have? 1 and 4 is 4. Then we have 20. Then we have 12, 24 minus 24 is equals 0. We move yellow to the right. Then we have 8. And then we have 20. And the last one is 28 minus 28 equals 0. And then we move yellow to the right again. 4 plus 25, and then minus 28, which makes 1. So what do we have? We have 1, 1, 1. So it is an identity matrix. They have not lied. Okay, but the other way around as well, right? Yeah, I think this technique is quite good. Let's try to choose different pen. Okay, this time B times A. B times A. So let me put the color in. Okay, what do we have here? Minus 7, and then minus 28, minus 36. Yeah, that's, no, it's not minus 26, it's plus 36, which is exactly the same equation as the other one. Yes, because I'm doing stupid things here. I need to actually change those two. Like this. Now we have a different equation. So at this time we have 7 plus 4 plus 4. Oh no, minus 7. Yes, this makes 1. Do we had this equation? Yes, we had this equation here. Okay, let's just continue. So now we have to move yellow 1 to the right. And then we have minus 7 again. This time plus 2 and then plus 5 equals 0. We move yellow to the right again. Then we have 6 minus 2 minus 4 equals 0. So do we have these equations somewhere? We have something similar here. And we have this one here as well. So I pretty much think that this is the determinant. Like at least there's some kind of connection. The 3 times the 3 times 3 determinant is the calculation is a bit different. I can't remember how it was, but I think this is the same thing because you're just you're just rearranging the elements. Okay, let's continue. Now we have to move green 1 down, goes to the middle. And then we have minus, what is it, 28. Then plus 8. Plus 20 is 0. Then yellow goes to the right. Then we have minus 28. Plus 4. Plus 25 makes 1. And the next one is 24 minus 4 plus 20 equals 0. Then the last part is to just move it down. Yeah, 6 times 6 plus 6 makes 42, and then minus, and the next one is 14 plus 14 and plus 28. Yeah, we remember these numbers. This is 0. So the next one is it is 42 again, minus 42. Then we have plus 7 and plus 35. That makes 0. And the last one is 36 minus 7 minus 28. That's 1. And we see we have the identity matrix again. Cool. Okay, we can say this is correct. So now 2.4 definition. Transpose. For matrix A in Rmxn, the matrix B from the set of matrices n times m. So it's flipped. What I mean is this one and this one. The n is connected. Again, for A, the matrix B with Bij equals Aj I, so it's kind of reversed, is called the transpose of A. We write B equals A transpose. In general, A transpose can be obtained by writing the columns of A as the rows of A transpose. The following are important properties of inverses and transposes. Okay, so what they mean, first before we go to these properties, this is basically the definition, right? So one thing you can think of, if I and j is the same, then nothing changes. So B11 equals A11 and B22 equals A22. So if you have a matrix, all the lines in the middle are the same. And then if we have, let's just call them, yes, and then we go here, G, H, I, J, K, L. So what happens is we are flipping these two, 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 we are flipping these two and these two. So it is like a mirror image. Every element will get flipped. It is some kind of, yeah, it's like a mirror. That's how I always saw it. I'm not sure if this intuition is somehow helpful, but this makes the transpose quite easy to understand. Also, it is if you flip rectangle like this is the diagonal, flipping it. So this would mean, not sure if I have here flip or something like that. No, I can't. I'm not sure how to rotate that. But what that mean is, let's just draw it in a different color. That you would flip it somewhere, something like that. It's not big enough. Something like that. We'll go a bit down. I think like that. Yeah, it's quite interesting. So if you see it as a sheet of paper, then you have to flip it through the third dimension. You cannot just rotate it. That's what I would see it. That's how I would see it. But yeah, actually just if you want to have the rectangle shape, you can, but if you want to actually flip the whole sheet, then it has to go through the next dimension. I'm not sure, maybe it's just how I see it. Okay, so this is the transpose. The definition is more complicated than the intuition in my view, but you need to have a definition. Okay, so here we have some properties. So the first one is easy. The second one is interesting. So if you multiply and then have the inverse of it, it's the same as you would inverse each one of those in reversed order and multiply. Like, I'm not trying to become a mathematician here, just to understand enough to do machine learning. So I guess I would just memorize these. Maybe the intuition will come later. So it's the same as, oh, okay, so then the third one is if we add the matrices and then take the inverse, this is not equal to doing the inverse of each one and then add, but have the same order, not like before, where the order is flipped. But I think the flipping order does not make sense for addition. Does not it's not revel. Yeah, A plus B has to be B plus A, because we are putting these two matrices on top of each other and punch through each element basically. So if the first sheet is on top, or the first matrix is on top or not, does not make a difference. Okay, so the fourth one is, yeah, if you transpose this 2 times, then you're going back to where you started at. It's obvious. What's not obvious is A times B transpose equals B transpose times A transpose. Well, the multiplication makes sense in this, like the multiplication here. At least it will work out because we are flipping the dimensions. So if you would start with dimension 2, 3, A, and then B 3, 2, you would end up with A times B, so a 2 times 2 dimension. And if you flip it both times, you would have a dimension of, again, maybe. So if you have dimension, you have the dimension 3 times 2 for A and 2 times 3 for B. In the end, you would come up with 3 times 3. If you transpose each of those first, you would have a dimension of 3, 2, 2, 3, and 3, 2. Well, it makes no sense. You will end up with a dimension of 2 times 2. And they cannot be the same. Okay, I have to make a mistake somewhere. Okay, let's write it down again. We have a matrix A. Matrix A is an element of R, does not matter, 3 times 2. And B is 2 times 3. So if we do A times B transpose, so we do A times B transpose, this must be a matrix of element 3 times 3, and then we transpose it, which still makes it 3 times 3. And if we do B transpose times A transpose, if we transpose B, we will have, we flip that, we flip this one, and this one is flipped too. So 2 times 3, and this one would be 3 times 2. So we have 3 times 2 and 2 times 3, which equals 3 times 3. Makes sense. So at least we know that the dimensions, they make sense. It's quite easy to get confused here, even though I really don't know why. Like, I can add dimensions up, okay, but this does not give me any real intuition. Okay, so the last equation is A plus B transpose equals A transpose plus B transpose. So if we take our punch hole example again, so you have one matrix, and then you take your second matrix, you move them on top of each other, and then you punch the holes to do the addition. and then whatever the result is, you flip. So basically transpose. This is something you can see. Yes. Okay, you have a result. If you transpose each one of those and then you do the addition, then yeah, that's the same thing. I think I have the intuition for addition, but not for multiplication. I hope um, I will develop the intuition for multiplication, because once you have it, it's so obvious. If you don't, then you have no idea what you're doing. At least that's for me the case. Okay, so I think I will have to memorize those two. Okay, so next point is the definition 2.5, symmetric matrix. A matrix A, element of R n times n, is symmetric if A equals A transpose. Yes, note that only n times n matrices can be symmetric. Makes sense because otherwise the shape would not be the same. So it has to be a rectangle or rectangular shape. Generally, we call n times n matrices also square matrices because they possess the same numbers of rows and columns. Yes, that's what I meant with rectangle square. I guess rectangle is more than a square, right? Yeah, of course. Okay. Moreover, if A is invertible, so A has an inverse, right? Then so is T transpose. Okay, so transposing does not take away the invertibility. So if A is invertible, then is A transpose also invertible? I do not understand why they are writing this here. Is this only for square matrices? I mean, they said before A equals A transpose if it's a symmetric matrix. But if I read this correctly, this one, this is just a new property. It says that every matrix which you can invert and transpose is equal to if you transpose the matrix and then take the invert. Okay, not every matrix has an inverse. This is what they said before, right? Yes, here we have it. If this inverse does exist. So if it does exist, then the transpose of it is also invertible. So you have a matrix A, you invert it, and then you transpose it, and then you say this is the same as A minus transpose, minus T. And it does not matter if you transpose it first and then invert it, or you invert it and then you transpose it. I think this is true for, well, okay, in the case it's not a square matrix, can that be? The inverse has to be the same dimension, right? Okay, something I have overlooked is this point. It says that consider a square matrix A. So the whole inverse case was made from for the inverse of a square matrix. If the matrix is not a square, can we do then the inverse? Even the example had a square matrix. So I pretty much assume from this point here that the inverse can only be can only exist for a square matrix, which means that at 2.5 we're here. That also this whole thing here. So A has to be a square matrix. So if you have a square matrix and it has an inverse, and then you transpose it, it's the same as if you transpose it and then take the inverse. Okay, let me clean this up. So what's important? Let me mark that important part. Of course, the definition is important. Then the last sentence here. Okay, so last sentence, remark sum and product of symmetric matrices. The sum of symmetric matrices A, B of a square matrix is always symmetric. However, although their product is always defined, it is generally not symmetric. Okay, so you have two square matrices of the same dimension. If you add them together, then the sum is always symmetric. But the product is not always symmetric. And the product has to be the same dimension. I can't see why that's true. It's not obvious for me why this is true. Okay, in case for addition. Okay, what they're saying is symmetric is if A equals A transpose. And here we have the case of A and B. A and B. Let's flip A. Let's do A transpose in our head. Yeah, it's still the same. And B is also the same. If we add them together, you would have something like, and then you flip them, and then, yeah, this is also transpose. Like I can do the calculation in my head here for addition, but I would not understand why this is true for every case. Let's try to figure it out. Okay, let's take, oh, I see. The sum of symmetric matrices A and B. So A and B, they have to be symmetric. Yes, if they have to be symmetric, then the sum is also symmetric. Now I can see it. So I imagine these ones here to be somehow connected on a line and able to rotate around this line in the third dimension. A deck, like a card, and you just rotate it. So if I stack them together, like I'm adding each element, then it's still symmetric. For multiplication, it can be, it cannot be, okay. Yeah, I think this is also important to remember. Yeah, so with this we conclude this one little chapter. This took quite a while. Yeah, so see you next time.